Okay. All right, so what do we do here? We're looking at an absolute value equation. Add 5, good. Okay, so we're going to add 5 to both sides. Four times the absolute value of negative 3x minus 6 equals 0. Okay. Divide by 4.
0
Okay, and so we end up with the isolated absolute value. So the absolute value of negative 3x minus 6 equals 0. Okay? So then what's the deal? If it's equal to 0, do we end up with 2 equations this time?
No.
No. Okay, good. Only one. Now normally if that were like 10, we'd get whatever's inside equals 10 or whatever's inside equals negative 10, right? But in this case, positive and negative 0 doesn't make any sense. We just get 0. So we come up with a single equation, but now it's a regular equation. Right? It's no longer absolute values, so we can just proceed with normal algebra. Last 2 steps.
Add 6.
Add 6. So I got what, negative 2? Do you agree?
Yep.
Okay, and then on a test, of course we want to check this. It's a checkable solution. This one, you probably don't even need to put this in, really, right? I mean, into Desmos, but we can. So if let's type out the expression first. There's the absolute value bars. Everybody see that? Little button there, that's convenient. So we get 4 times the absolute value of negative 3x minus 6 minus 5. And then let's go back and replace the x with the quantity negative 2. And we get negative 5. Well, that's what we should get. On the right side we have a negative 5. So it works, doesn't it? When we plug in negative 2, we get negative 5 equals negative 5, which is true. So we just effectively checked it. Okay? Oops. How about that? Maybe. Tell you what, let's skip that one. I'm confident you can do that one. Okay, here's what we started on yesterday. Let's finish this one. So we got a solution on this. We got the answer. We went through all the algebra, and we got the solution. A is greater than or equal to negative 1/2. So if we were to graph that, it looks like this, doesn't it? Okay, so here's the part where I want to show you. This is something a little different. You got to really pay attention to how would you check this effectively with a calculator, with some kind of technology. So we would check, first of all, what we do is we'd say, okay, well, what's the boundary of our solution? Well, the boundary is negative 1/2. So you always check the boundary value. When you plug negative 1/2 back into the original inequality, you should end up getting the same number on both sides of the inequality. Okay, that's the first thing that has to happen. And here's how you can kind of, I'll finesse through a little argument for why it's that way. What if this were an equation instead of an inequality? Would any of the algebra really have changed? No. I'm going to end up with the same answer at the bottom, only it would have been an equal sign, right? How would we check this if it were an equation? Well, we'd plug the value back in and get the same number on the left and the right. Okay? It's an inequality, though, so we've got to do a little bit more than that. We're still going to plug in the boundary value, and let's verify that that works. So we've got our left expression, 3 times the quantity 3a minus 7 minus 6a. And then the right expression is 5 times the quantity a minus 4. Let's go back and exchange the a's for negative 1/2. And we got to put those in parentheses, right? Okay, so we get negative 45/2 on the left side. How about the right side? Negative 45/2. So So we know the boundary value works, right? But now we need to verify that some other value works. So the solution should be values of A greater than or equal to negative 1/2. So the boundary worked the way it should. What's another test value that should give us a true statement? 1. Or even an easier one. 0, right? 0 is greater than negative 1/2, isn't it? Okay. So we could just go back, and you probably don't even need the calculator for this, but it's easy to do. I can just replace the negative 1/2 with zeros and get the answer negative 21. Okay, did it work? We got different answers. Does that mean it's wrong? No, we expected that to, correct? What we wanted to have happen was this is the left side of the equation, correct? In fact, let me take a picture of this. Right, so there's my picture that we're using to check. So put it right there. Right? Okay, did it work? Well, this is supposed to be the left side. So when we plug these values back in, we're getting something like negative 21 is less than or equal to negative 20. True or false? True. It worked then, didn't it? See, we just proved both parts of that. When I plugged in the boundary value, I got the same number on both sides. And when I plugged in a point to the right of the boundary value, it gave me a true inequality. Okay? Everybody get how you do that? So that's a great way to check inequalities using decimals. Easy to do. You can know immediately, not immediately, but you know that you got the answer right, so don't roll the dice on it. Just know it's right before you submit it. Okay, check the boundary value and check a value either to the right or left of the boundary value, depending on what the solution is. Okay? Questions? Okay? Yes?
So how would you check if it was just greater than? If A was just greater than?
Okay, if it was just greater than, when we put the original problems in, we would have gotten the same number on both sides, right? Which, now that wouldn't have been true, but it still would have verified that the inequality was doing what it was supposed to do.
Okay.
You understand what her question is? What if this didn't include an equal sign? Okay, then when we plugged in our, what did we get, negative 22.5? Is that what it was? What the original one was? So when I plugged in the boundary value, I got negative, was it 45 halves, right? I got negative 45 halves on the left is less than or equal to negative 45 halves on the right. Yeah, that's true because they're equal, but what if they weren't? What if that was just a less than? It still tells us what we need to know, because if I had graphed this thing, what I would have gotten then is I would have gotten the solution that would have looked like, I would have gotten the solution A is greater than negative 1/2. And so it would have looked like this, right? So any value greater than 1/2, negative 1/2 should have worked. Negative 1/2 should have failed, but it should have been the boundary between working and not working. So you see what I'm saying? So even though that's not a true statement, negative 45 halves is not less than negative 45 halves, it makes sense that that corresponds to the open endpoint. Right, so you still want the numbers to be the same on the left side and the right side to verify that it's working. That make sense? Okay, all right. Okay. Okay. I mean, we can do this one real quick. You can just tell me how would I check this. Maybe we don't have to even go through the whole thing. So what do I do to isolate x?
Subtract 6.
Subtract 6. Negative 55. 50, now what?
Divide by
Did I do that right? Yeah, I did.
Yep.
Okay. Divide by negative 10.
Yeah.
Okay, so we get x, we get positive, what, 11 halves, is that what that is? And I get positive 5. What else?
Switch this
Yeah, flip the signs, good. Okay, and that should be equal to, shouldn't it? Yeah. Okay, so that looks goofy, what should I do to that?
Flip it.
Gotta flip it around, good. So we got the x, 5 is less than 11 halves, so 5 should go on the left. What's the relationship there? X needs to be greater than or equal to 5 and less than 11 halves, okay? So how could I check this one? Yeah, okay, everybody see that? So on this one, I'd have to verify I've got two boundary values, don't I? If I look at what the solution looks like, in the graph of the solution, there's 5 and there's 11 halves, and I'm doing that. Oops, other way around. Right? So I got two boundary values to check. If I put 5 in, I should get the same number on one of those inequalities should give me the same number. Agreed? And if I put 11 halves in, the other inequality should give me the same numbers. And then if I put a value in between, I should get a number that's true throughout the entire inequality. Let me just show you what that means. Okay, so we've got the expression, we got three expressions, right? We've got, well, I can just do the middle one and I'll compare it to the numbers. So we've got the expression 6 minus 10x. Okay, and if I replace the x with a 5, I get negative 44, right? So that fits. So that matches this endpoint. Agreed? Okay? If I put in, if I change that 5 to an 11 halves, I get the other endpoint. So that checks, right? When I try the two boundary values, I get the two endpoints. And now I just have to try a value in between. Well, let's just put a decimal in. What's a decimal between 5 and 5.5?
5 1/4.
5 1/4, okay? So what if I put in 5.25? If I put in 5.25, I get the answer negative 93 halves, which as a decimal is negative 46.5. Is that in between those values?
Yes.
It worked. See what I'm saying? It worked. Okay? Easy way to check it. Okay? Okay, one of these and probably call her good. So what do I do first?
Add 3.
Add 3. And divide by 2. Everybody agree I get the absolute value of negative 2x minus 4 is less than 12? Okay. So what does that become as an absolute value, or as a compound inequality?
It's greater than negative 12.
Okay, good. Let's say it that way. Greater than negative 12 and less than 12. That's an and, right? Compound inequality. Last couple steps. Add 4. Negative 8, negative 2x, 16. Divide by negative 2, good. So I get x, 4, negative 8. Flip everything, very good. Okay, turn it around, good. So x is greater than negative 8 and less than 4. Okay, and then we check it the same way, wouldn't we? Right, but on this one, okay, so what's gonna happen this time? If I'm checking those values, so these are the values I'm checking. What do you predict's gonna happen this time? When I plug these in, we'll just see, you can verify this for yourself, but what's gonna happen? Putting in this expression on the left, correct? Okay, so I've got 2 times the absolute value of negative 2x minus 4 minus 3, right? We're going to plug in, let's plug in one of those boundaries. Let's plug in negative 8. Oops. What do you know? 21. Checks out. What's going to happen if I put in positive 4? 21. What do you know? Okay, so both of those boundaries give me 21. What if I pick a value in between, like 0 would be a convenient one?
It's gonna be less.
It's got to be less than 21. And it's 5. 5 is less than
So does it
21.
look like that?
Yeah, because remember, it's a V, right? It's a V. So in this case, it's actually more convenient in a way. When we plug in the boundary values, we should get the same thing, same number on the left and right, but when I pick a value in between, it's going to give me a true inequality. Okay? I mean, do you have to do this stuff? No. I mean, it's just, but it's smart to do. Okay? It's smart to check your work, especially on tests. Okay? Make sense? Go. You can work. You can test.
Do we have to turn around?
Yeah. Go